log base 10. This is in the saturated solution. And then just solve for the silver ion concentration in the saturated solution and then figure out how that relates to solubility. Once we have that, we can calculate the KSP. Because for every silver ion, I'm going to generate an iodide ion. So the silver and the iodide concentrations will be the same. Examples worked in the book. Here are some electrodes here. You know, this is silver with a coating of silver chloride. Here. Some other electrode. I have to look that up. Silver chloride and HCl. These are pH probes here. These are electrodes that are used for pH measurements here. For pH measurements, you have this glass membrane here, this glass. The glass, it's glass, but you know, there's so many different formulas of glass. A lot of people, when they think of glass, they think it's a complete insulator, but these glasses are sensitive. They can carry a very, very small current.
Why is E not cell 0 volts?
Because E naught means under standard conditions. So if it's standard conditions, you'd have 1 molar silver ions here versus 1 molar silver ions here. Standard means 1 molar, 1 molar. If there's a tug of war between 1 molar silver ions pulling electrons this way and 1 molar silver ions pulling the electrons the opposite way, who's going to win? It's going to be a tie. Therefore, it's 0 volts. pH probes are going to have this glass. This glass, you know, but glasses have very slow response. This is why the pH probes continually have to be soaked, because what you need is you need a saturated membrane on the end. If these pH probes dry out, then the response time becomes very long. Rather than getting a pH measurement in seconds, you get a pH measurement like in 10 minutes, you know. You got a dried out probe. So these probes always have to be maintained. And then there's going to be a concentration of ions inside versus concentration of ions outside. The glass happens to be sensitive to hydrogen ions or hydronium ions. And so that's going to change the charge on the outside versus the charge on the inside. And that generates a voltage or a potential. You know, having a charge difference is a voltage as well. And so these are different probes, or common probes here, electrodes. Here's a pH meter with a glass probe there. And so some of the reactions that are occurring here. But we're going to not get into this. Just skip it. But you could read about it. Nowadays they have solid state probes as well. This is pretty much the most common probe here. If you look at it, what's the oxidizer in this particular reaction? Yeah, it's this is kind of tricky because there are multiple reactions happening here. This is the glass membrane one. This is, you see the glass membranes here. H plus. Yeah. You see, this is chloride. And this unusual redox. This would be redox. We need something pulling the electron as well. The electron has to go somewhere. The electron is going to go to AgCl, Ag, and chloride. So we're back to the beginning. But over at the other electrode, we have this difference. And so H plus within the glass, H plus outside the glass. And we generate a potential difference. So it's a bit more complicated. We'll skip it. Instead, we'll look at batteries. Primary cells or disposable batteries. Once the voltage has gone down to, we can call it dead, and throw them away. The reason is the reactions are not easily reversible. Very difficult to reverse these reactions. Secondary cells, cell reaction can be reversed by passing electricity through the cell. We can recharge these batteries. The problem with recharging is some of the things aren't so easily reversible. Like, for example, if one of the electrodes is metal and you eat the metal away, that is, the metal becomes oxidized. When you recharge it, and you coat it, let's say you recharge it, you start plating metal on metal, and then sometimes it's not quite as far as the solid form goes, it's not quite the same. And so this is like if you're trying to recrystallize something and you get even worse crystals than before. And so secondary cells have what's called a cycle time, like a lifetime. How many cycles, how many times can you recharge it before it's dead because things aren't perfectly reversible? A little bit of entropy gets in there, whatever. And so they aren't infinitely, and so they suffer the same fate eventually as primary cells. You can't reverse it anymore. Secondary cells, but some batteries you can cycle maybe 1,000 times, which is huge. So I was reading something about the cycle time of the iPhone battery, and it's designed to last, I don't know, a couple of years, and then that's it.
Wait, a couple of years?
Yeah, something like that.
And then it's gonna be dead forever?
Well, it's just gonna continually lose energy content. You aren't going to be able to get as much light out of it. And so it might have light, they say, of 6 hours or something, and then it goes to 5 hours, and then 4 hours, and 3 hours, because each time you recharge it, it doesn't quite go back to the beginning. And then we have flow batteries or fuel cells. Fuel cells, you don't have to recharge. What you do is you just replenish. You remove product and you replenish reactant. And so fuel cells are like a car. A car you just replenish the fuel, which is gasoline, right? That's what you do in a fuel cell. You just replenish the fuel, which is generating electricity. A primary cell is like if the gasoline tank was sealed, and once you used up that tank full, you just throw it away. Secondary cell is you have to hook it up to some and regenerate. So you take the CO2 that you formed in the water and then reverse that reaction to make the gasoline. Is that a reaction that's easily reversible? No. But if it were, then we'd have something like this. And so this is the most common primary cell. This is a heavy-duty battery. A heavy-duty battery like this is going to have a graphite rod, which is the cathode. Now, graphite rod, if you see graphite, is that inert or is that a reactive electrode? That's inert, Graphite rod's got to be feeding electrons to the oxidizer. And so what is the oxidizer here? Well, if we look at the oxidizer, what's surrounding the electrode? And if we look, MnO2. MnO2 is a solid, also called desert varnish. It's MnO2. And carbon black paste. Carbon black paste is graphite paste. One interesting thing about graphite is solid graphite is an electrical conductor. And so if you have a paste of graphite with MnO2 crystals sprinkled in there, then MnO2 is an oxidizer because manganese is in +4 oxidation state. And so this is a decent oxidizer. But how is the MnO2 going to come into contact with graphite? MnO2 is a crystal, it's not moving. And if this were, this is like a semi-solid here. If this were a liquid, all the MnO2 would just sink to the bottom, right? MnO2 itself is not a very good conductor. And so what you have is you have MnO2 sprinkled in this paste. The paste is actually an electrical conductor. And so the electrons can be transferred from the graphite to the paste to the MnO2 crystals if the MnO2 crystals aren't in contact. If some MnO2 crystals are in contact with the graphite, then electrons can be transferred from the graphite directly to the MnO2. And so they're using a solid oxidizer here. Now, why use a solid? There's a huge advantage to using solids in batteries. And that advantage is, does the activity of a pure solid ever change? No, activity of solid stays the same. So even as you're consuming the MnO2, the concentration is not changing because the activity stays 1. That means the voltage is not continually dropping. And so the reason they try to use as much solid or as many solids as possible is and liquids is because of the activities. And therefore the voltage should be fairly stable. Okay, so we have MnO2 as the oxidizer. What's the reducer though? And so those electrons are coming from somewhere. And so electrons are being fed to the cathode here from the anode. The anode is a steel container here. And the steel container is not going to be giving up electrons so easily. But inside the steel container, it's coated with zinc. Zinc is an excellent reducer. Steel is not. And so what's going to happen is the electrons are being pulled over to the cathode through the steel. The steel is going to act as an electrode, as well as zinc. And so the electrons are coming from zinc. So zinc metal is going to go to Zn2+. And then we need a salt bridge. Well, the salt bridge in this case is just a paste. No, it's a semi-solid. And it's just going to be an ammonium chloride, zinc chloride salt bridge. But this salt bridge is very interesting because this salt bridge doesn't consist of inert salts. This salt bridge consists of reactive salts. And the salts that were chosen for the salt bridge were chosen for a very specific reason. And so let's take a look at the half reactions here. And so at the anode, oxidation occurs and we generate the electrons. The Zn gets oxidized to Zn2+ plus 2 electrons. The 2 electrons goes through the steel container, out the bottom, and through a wire or circuit to the top, which is graphite. And from the graphite, they're either fed to the graphite paste, the carbon black paste, or directly to the MnO2. And if they're fed to the paste, then eventually they'll make their way to MnO2 crystals, where they're consumed. There's going to be a little bit of water because it's a paste. It's a semi-solid, right? Those 2 electrons plus water plus 2 MnO2s is going to yield Mn2O3. And so we're going from +4 manganese to +3 manganese, right? And 2 hydroxide. Now what's going to happen as the cell operates? Well, this is activity 1, activity 1, activity 1. This is AQ. This is activity 1. This is AQ. So what's going to happen as the cell operates is the zinc 2+ ion concentration is going to grow. The hydroxide ion concentration is going to grow. Therefore, Q is going to get bigger. There's more products. As Q gets bigger, what happens to the voltage of this battery? It goes down. And so immediately when you start this battery, it's going to lose its voltage. But I told you they chose the salts for the salt bridge very carefully. And so they used ammonium ion in the salt bridge. Well, ammonium ion is going to have 2-fold purpose. 1 is to neutralize the space charge. 2 is to react with hydroxide that's generated. The hydroxide that's generated will be converted into ammonia. But ammonia gas is a problem, right? Because 1, you're going to generate pressure inside the battery, which can be an explosion hazard, a pressure bomb. 2, whether it's concentration or pressure, both are going to decrease the potential because Q is not QC, it's not QP, it's QEQ. QEQ takes into account concentrations and pressures, right? But we also have this. This is a combination of what? What kind of reaction is that? Yeah, it's a metathesis and well,
Ligand base.
yeah, what's that called? Reaction is that? Yeah, we have complex formation, which is AKA.
That's weird. I never seen this before.
Well, that's because we would separate it. We'd separate this into two steps. The two steps we'd separate it in is one. First we have a reaction between two amines and a ZN2+. Two amines and a ZN2+ would be called a Lewis acid-base reaction, followed by this cation, which is diamine zinc, precipitating out with chloride, which would be called a metathesis. So this is just adding up the Lewis acid base and metathesis to get the net reaction here. But take a look at what happens. We get rid of the ammonia gas and form a solid. And so let's take a look at the net reaction. When we add everything up, they didn't give me that. But we could do it. Let's do it on the board. How about that? Or what? Can you write down the net reaction for me? Just add up those reactions and see what happens.
Hey, you add the oxidation reduction and the acid base and the precipitate?
All of them, yeah.
So it has a law problem? It has a law?
You kind of like it Hess's law, right? Exactly. Except we're just adding up the reactions. We aren't adding up any delta H's or delta G's or anything like that.
I think you just cancel one hydroxide, you don't multiply the second one. I don't want to how you asking you. I think you just cancel one. Professor, on the hydroxides,
Yeah.
for the acid-base reaction, do you have to multiply by 2 or do you just remove one hydroxide? It's just remove one, right?
Well, do it and see. What do you think? You know, if you're a battery designer, what do you think you'd do? Would you just leave one and say, oh well, halfway is pretty good enough. I made it halfway. Or would you try to go all the way to solid?
I'll try and have it go all the way to solid.
Yeah, try to have it go all the way to solid and see what you get. Okay.
Would there be any intermediates?
Yeah, cancel out the intermediates.
Is the NH3 on number 4 a gas or aqueous?
It's number 4.
Gas.
Gas.
Gas and aqueous. NH3 is very soluble in water. Somebody have it? You guys have to be careful because is that reaction 2, is that balanced? No, we need to balance it. How can I balance it? I need, it looks like I need 2 H2Os, right?
Yes.
So 2 H2Os cancel out 2 H2Os, 2 hydroxides, 2 hydroxides. Zn2 plus cancels out Zn2 plus. So I'm going to get 2 ammoniums from the salt bridge, 2 chlorides from the salt bridge.
Number 2 is balanced because you've got 5 oxygens and 2 hydrogens on each side, right?
Oh yeah, you're right, it is balanced.
And the
It's balanced. How about number 4?
No.
No, number 4 needs to be balanced.
2 ammonia and 2 CO-.
Yeah. So I'm gonna end up with 1 water. Okay.
Yep.
Okay.
So right there.
So I'm gonna get the. This is gonna go 2 ammoniums, 2 chlorides goes to.
And then 2O3.
And then 2O3 solid.
I think I got 1 H2O and then the complex ion.
Plus an H2O
Yeah.
plus the complex Zn and H3 2 Cl2.
Yeah.
Okay. Well, H2O isn't the problem because H2O is a pure liquid. So does the activity of a pure liquid change?
No.
No. And then the problem is going to be with the ammonium and the chloride. But one way to make this a non-issue is to do what?
Evaporate out of water.
No, we don't want to evaporate all the water, but one way to make ammonium and chloride a non-issue is by using a trick, using kinetics.
Wow.
pseudo M order. What's that all about? Pseudo M order. You remember that? One way of making this non-issue is keep the concentration so high they don't really change. So you have a concentrated salt solution in here, and therefore, as the reaction progresses, the concentration of these two barely change. Therefore, it's not going to impact the overall voltage. And so the voltage will still be stable. It's not perfect. Eventually this will die because we're going to run out of reactants, right? Or the voltage will drop because these issues. But essentially the purpose is prevented. Now alkaline cell is much better than that. An alkaline cell is going to have, rather than ammonium chloride, it's going to have some hydroxide in there. If we have hydroxide in there, in the salt bridge, if there's hydroxide in the salt bridge, then instead of doing this to precipitate out the zinc, we could just use hydroxide to precipitate out the zinc. And so if you have hydroxide or alkaline in the salt bridge, then immediately when the Zn2+ is produced, it comes into contact with the hydroxide and precipitates out white zinc hydroxide, PBT. And that white zinc hydroxide, PBT, yeah.
Color? When the batteries start leaking, that's what's coming out of them?
That could be, or it could be other stuff as well, sodium hydroxide or whatever else. I think they use sodium. I don't know if they use it. Most likely sodium, it's probably the cheapest. But this is also going to produce hydroxide. So in the salt bridge, if you have something like sodium hydroxide, we consume hydroxide on one end and we produce it on the other. It's fine.
Excuse me, why would the two zincs cancel out of each other? I see there's one zinc aqueous left.
Oh, because immediately when the Zn2+ is formed, immediately when it's formed, it's reacted
It's reacted with the
with the OH minus. And so here's a redox followed by metathesis. We're going to get Zn hydroxide. And so we just add them up. It's like sulfides. Immediately when sulfide is produced in water, it reacts with water to form HS minus and OH minus, back in chapter 18. So the same kind of deal. This is a car battery here. These batteries, you don't have to memorize the operation, the batteries. You don't have to memorize the cell reactions. You just know the strategy. What is the strategy in making a battery? You want
potential differences.
well, not always the strongest and the strongest, because strongest are hard to contain. For example, if you have the strongest, it'd be fluorine gas, and the strongest lithium metal, it would be a very dangerous battery. But you want solids and liquids so that the voltage, most electronic equipment requires a minimum voltage to operate. If you drop below that minimum voltage, it doesn't work anymore. When you throw away your batteries, they aren't completely dead. The cell is not zero when you throw away your batteries. You throw your batteries away when the voltage, like a standard AAA battery or AA battery is 1.6 volts, 1.5 something volts, right? But by the time it gets to 1.3 volts, there's still plenty of life in there, right? But that's
Doesn't work for your machine.
it doesn't work for your electronics. You throw it away, unfortunately, right? And so this is why the voltage is so important. There's still life in that battery, but, well, not much, because once it hits that, it's precipitously drops, because the voltage stays fairly stable and precipitously drops. There's a car battery. Car batteries are secondary batteries. Those are primary batteries. It's a secondary battery because it can be recharged. So here they're just showing it recharge. You recharge a battery by forcing electrons to flow backwards. And so normal operation, the cathode, cathode sucks in the electron, the anode pumps out the electron. Over here we have lead as the anode. The cathode in this case is very interesting. The cathode is lead-4 oxide. And so lead-4 is a pretty strong oxidizer. So lead-4 is oxidizing lead metal from lead-2+. And so here's the cathode. And so as this discharge is, the lead being converted into actually lead metal. This lead is being converted into lead ion. once the voltage drops to a certain point, it's no good. You have to recharge it. To recharge it, you have to hook up an external power supply. External power supply pulls electrons off the cathode, and so forces whatever the oxidizing agent was to become oxidized itself by regenerating this, and forces electrons on over here. So any lead ions that were generated would be reformed back into lead. But do you think you're going to get these nice, like honeycomb or whatever, checkerboard electrodes? Will the leads nicely position themselves? When the lead ions crystallize into lead metal, are they going to form this nice checkerboard pattern, or is it going to be much more? It's going to be much more random, right? And so, car batteries are going to have a certain cycle time. And it depends on how much material and other stuff. But car batteries are rated how many months they expect them to survive. As far as that, here are the half reactions here. Now, the half reactions are tricky because you got to figure out how many electrons that were transferred in this half reaction. Can you tell how many electrons were transferred in this half reaction without somebody telling you? Well, yeah, you can by looking at the oxidation state. So here, lead 4 goes to lead 2. And then this stays the same, sulfur +6, sulfur